Yes, so in last lecture we was discussing GL NF and SL NF, and at last we had derived the formula of order of GL N ZP. F is a field, and field is what? ZP, and SL N ZP. So let me just recall it, and I want to generalize that formula for arbitrary field, right? So in last lecture what we derived, order of GL N ZP is what? It is P raised to N minus 1 into P raised to N minus P into P raised to N minus P square into, and so on, P raised to N minus P raised to N minus 1. And order of GL N SL and ZP is what? It is simply order of GL and ZP divided by P minus 1. So if I write explicitly, then it is P raised to N minus 1, P raised to N minus P, P raised to N minus P square, and so on, P raised to N minus P raised to N minus 1 divided by P minus 1. So this is the formula of order of GL and ZP and SL and ZP. Here ZP is what? Here ZP is field having P elements, and of course P is prime. P is prime. Now we know that if F is in field, F is any field, implies cardinality of F is what? It will be of the form P raised to N for some P prime, for some prime P, and for some N belongs to N. So here we have a particular case. My F is what? F is ZP, where ZP has P elements. Cardinality of ZP is P. Now if I replace this ZP by arbitrary field, then what is we have? The structure is GLN F, where F is a finite field. Any finite, I have to write any finite field. That if field is infinite, then its cardinality is obviously infinite, but if F is any finite field, then its cardinality is equal to P to the power n. It is a power of single prime. So now my question is, what is the cardinality of GL and F, where F is any finite field? So it is simply generalization. So this is what here. What is P? P is the cardinality of ZP. So here what is F? F is field. So you just consider cardinality of F to the power n minus 1, cardinality of F to the power n minus cardinality of F, cardinality of F to the power n minus cardinality of F square, and so on, cardinality of F to the power n minus cardinality of F to the power n minus 1. So this is the general formula, and order of GL SL and F will be cardinality of F to the power n minus 1, cardinality of F to the power n minus cardinality of F, cardinality of F to the power n minus cardinality of F square, cardinality square of cardinality of F, and so on, cardinality of F to the power n minus cardinality of F to the power n minus 1 divided by cardinality of F minus 1. So this is the general formula of cardinality of GL and F and order of SL and F, where F is any finite field, right? So if you take cardinality of F is equal to P, then we have this one. So in last lecture we had discussed up to here, but this is just a generalization of these two formula, so please you keep this thing is in mind. Okay, so now we'll move for the fundamental theorem of finite abelian group, right? So what is that fundamental theorem of finite abelian group? See, when we in the beginning of the this course group theory, we focused on Zn, right? The Zn is a group with addition modulo n, and we know so many things about Zn. It is a cyclic group, its order is n, what is the form of the element, what is the order of every element, what are the generators, how many generators, what are the subgroups of Zn, which what is the order of subgroup of Zn. So we know everything about Zn, almost all information about Zn we have. Now if you consider any finite abelian group, then our fundamental theorem of abelian group says that any finite abelian group, see once again I am talking about finite group and it must be abelian, so any finite abelian group can be expressed as the external direct product of Zn's, right? Where n is some particular number, we will see in detail, but in short, if I roughly speaking, then any finite abelian group is the external direct product of Zn's, right? So that's why to handle any finite abelian group, if we handle Zn properly, then it is just a matter to handle the external direct product of Zn. So that's why we studied Zn in detail in the beginning of the group theory. So now let us see the fundamental theorem of finite abelian group. Okay, so to understand the fundamental theorem of finite abelian group, we need a concept of partition of natural number, right? So let us first of all define what is the partition. So definition: let n belongs to n. Let n belongs to n. A sequence of natural number say n1, n2, n3 up to nk. It is a finite sequence of natural number n1, n2 up to nk is called a partition of n if it satisfies two conditions. First one, n1 is less than or equal to n2 is less than or equal to n3 is less than or equal to and so on less than or equal to nk. So this sequence should be monotonically increasing, means it is non-decreasing, may be equal, n1 and n2 may be equal, n2 n3 may be equal, right? Second one, if you sum n1, n2 and up to nk, if you add all these positive integers, then it should be n. So then I will say called a partition of n if these two conditions satisfy, and partition and we write and this partition we write, and it is or you may say, and it is denoted by, and it is denoted by like this, n1 n2 up to nk. So if you have given n, so let me give one example. Let us consider with a simple example, say n equal to 3, right? So you consider n1 is equal to 1, n2 is 1, and n3 is also 1. So what I have, n1 is less than or equal to n2, less than or equal to n3, all are equal. So first condition satisfied. Second condition, if you consider n1 plus n2 plus n3, then it is 1 plus 1 plus 1, so it is 3. So these two condition is satisfied by 1, 1 and 1. So I will say this 1, 1 and 1 is a partition of 3, right? It is a partition of 3. Now if I consider n1 is equal to 1 and n2 is equal to 2, then first condition, n1 is less than or equal to n2, yes. Second condition, n1 plus n2 is what? It is 1 plus 2, that is 3. So two conditions satisfied by n1 and n2. So this 1 comma 2 is a partition of 3. Now you just consider n1 is equal to 3, only n1. This is what it is, a finite sequence. So it may contains only one integer, it may contains 2, it may contains 3, it may contains k, right? So n1 is equal to 3. So there is no n2, so no need to check this condition, first condition, right? And the second condition is what? The sum of all ni's, that is only n1, so it is 3. So both the conditions are satisfied, right? So this 3 is also is called a partition of 3. So I have 3 partitions of 3, right? So if you consider say 7, then you have 1 plus 1 plus 1 plus 1 7 times, then 1 plus 1 plus 1 plus 1 5 times, then plus 2. So you have here 3 has 3 partition, so 7 has some number of partition. So I introduce one notation. Let Pn n is what? N is positive integer. So Pn is what? Let Pn is equal to number of partitions of n के जितने partition मिल रहे हैं. So for example here P of 3 is what? Partition of 3 is what? Total number of partition of 3, and it is what? 3, as we have listed, right? So let us try to find out the number of partition of some integers. Okay, so let us start with 1. So what are the partition of 1? So it is only 1. 1 is equal to 1. 1 can be written only one way, it is 1. So partition of 1 is what? It is 1. P of total number of partition of 1 is 1. Now 2. So what about 2? Here n is equal to 1. Now you consider n is equal to 2. Then this 2 can be written as 1 plus 1. It is 2. Okay, let me write. Okay, fine. 2 is equal to 1 plus 1. And another way is 2. So 2 has 2 partitions. So P of 2 is equal to 2. What about 3? So you consider n is equal to 3. Then it is what? 1 plus 1 plus 1. So it is 3. Now it is 1 plus 2. 1 plus 1 is 2. And it is 1 plus 2, that is 3. So there are 3 partitions. There is no another way to express 3 as a sum of positive integers, sum of a sequence of positive integer, and that sequence is monotonically increasing, that is non-decreasing, and whose sum is 3. So these are the only 3 ways, right? Yes, see, 2 plus 1 is also 3, but it is not allowed because here n1 is 2 and n2 is 1. So n1 should be smaller or equal to n2. So here 2 is not smaller or 1. So that's why this way is not allowed. Right? So P3 is what? P3 is 1, 2 and 3. 3 partitions. Now n is equal to 4. So it is what? 1 plus 1 plus 1 plus 1. So it gives me 4. So that is the one way. Another way is 1 plus 1 plus 2. See, I'm following one pattern. You just first of all write down 1 plus 1 plus 1, whatever the number. Here 3, 4, 2. So you just write down n as 1 plus 1 plus 1 n times. Then you start to merge ones from the end. So 1 plus 1 is 2. Then 1 plus, you just merge 2 and 1, so it is 3. Then 4. Now you go at the second partition, and now you start to merge these two ones. So it is 2, 1 plus 1 is 2 plus 2. So now there is no other way to write down 4 as 4, so that these two conditions satisfied. So 1, 2, 3, 4 and 5. So there are 5 ways to express 4. So P of 4, number of partition of 4 is equal to 5. Right? Now let us see for n is equal to 5. So 5 can be written as 1 plus 1 plus 1 plus 1 plus 1, 1, 2, 3, 4, 5. Then 1 plus 1 plus 1 plus 2. Then 1 plus 1 plus 3. Then it is 1 plus 4 and 5. Right? Now let me start from here second. So 1 plus 1 plus 1, 1 plus 2 plus 2. I will not add these two, otherwise what happened? 2 plus 1 plus 2. So 2 then 1, 1 is smaller than 2. Now you look at here for the second this partition, 1 plus 1, it is 2 plus 3. And if you add here, then it is plus 5, so it is already there. So 1, 2, 3, 4, 5, 6, 7. So partition of 5 is what? It is 7. Right? Similarly, you can have the partition of 6 also. P of 6. So let us just try to write down what is 6. N is equal to 6. So 6 is what? 1 plus 1 plus 1. 3 plus 4 plus 5 plus 6, 1, 2, 3, 4, 5, 6. 1 plus 1 plus 1 plus 4 plus 2. Then 1 plus 1 plus 1 plus 3. Then 1 plus 1 plus 4. Then 1 plus 5. Then 6. Now you start with this partition. So it is 1 plus 2 plus 2. Then from here 1 plus 2 plus 3, and from here 2 plus 4, from here it is 6. Okay, so now again you start from here, it will be 2 plus 2 plus 2. So how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there should be one more. And yes, one more partition is what? It is a 1 plus 1 plus 1 plus 1, 1 plus 1 2, then 1 plus 2 is 3, 3 plus 1 4, 4 plus 1 5, 5 plus 1 6. Then from here it is 2 plus 2, then from here it is 2 plus 3, and from here it is 2 plus 4. Then from here it is 2 plus 2 plus 2, and one more. Yes, from here what we have is 1 plus 1 plus 1 is 3, and plus 3. 1 plus 2 is 3, so 3 plus 3. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So what we have? P6 is equal to 11. So see, this is what partition of n, and this Pn denotes P1, P2, P3, P4, P5, P6 denotes the number of partition of n. So let me make you one thing clear. There is no formula or there is no algorithm particular which gives all the list of all the partitions. So it is just by trial and error that you will get this many partition of 6 or 5 and like that, right? So you do not have any formula that partition of Pn is equal to some formula, so that you put the value of n and you will get P6 is 11. So this is one open problem, right? So if you list, let me summarize. So what I have, P1 is what? Total number of partition of 1 is 1. P of 2 is 2. P of 3 is 3. P of 4 is 5. P of 5 will be 7. P of 6 will be 11. P of 7, if you find P of 7, then it will be 15. P of 8 will be 22, and so on. So you just remember up to 1 to 8, and to remember P of 1 is 1, it is easy to remember because 1 has only one partition. Then if you look at 2, 3, 5, 7 and 11, then 2 is what? First prime, 3 is second prime, third prime, fourth prime, and this is fifth prime. And P7 is 15 and P8 is 22. So you just remember up to 1 to 8. We need up to 8 only. We will not require more than 8. So this is what partition of a positive integer. Now let us state a result in terms of theorem. So this theorem says that every finite abelian group is an EDP, external direct product of cyclic groups of prime power order. Every finite abelian group is an external direct product of cyclic groups of prime power order, and moreover the factorization is unique. The factorization is unique except for rearrangement, unique except the rearrangement of the factors. So let us first understand this theorem, but before that let me write this statement in other words. So in other words, let G be a finite abelian group. Let G be a finite abelian group. In other words, let G be a finite abelian group of order n, that is order of G is equal to n, then G is of the form Z p1 raised to alpha 1. So this is what of the form Z p1 raised to alpha 1. See, Z p1 raised to alpha 1. So it is of the form, see, it is like Zn, where n is p1 raised to alpha 1. So it is a cyclic group, right? And it is what EDP of cyclic group. So here every finite abelian group is EDP of cyclic group of prime power order, where p1 is prime. So alpha 1 is a power of p1 cross Z p2 raised to alpha 2 cross and so on cross Z pk raised to alpha k, where pi's are prime, not necessarily डिस्टिंक्ट, वो अलग अलग हो ऐसे जरूरी नहीं है. एंड अल्फा आई बिलोंग्स टू n. So let us first understand this statement. So actually this statement is what? It is up to here only. This is the another way of or another form of this statement. So what this statement say? Every finite abelian group is EDP. So you consider any finite abelian group. So here let G be a finite abelian group of order n. So let's say order of G is n. Then it is what? Is an EDP, external direct product of cyclic group. So it is external direct product. It is EDP of cyclic groups, and any cyclic group is of it is isomorphic to some Zn, right? And if it is infinite, then it is isomorphic to Z, but we consider only finite cyclic groups, right? So it is EDP of finite cyclic groups. I have to write here EDP of finite cyclic groups of prime power order. I think no need to write here finite, because cyclic group of prime power order means it is automatically finite. So EDP of cyclic groups of prime power order, right? And moreover, the factorization is unique except the rearrangement of the factor. Matlab, if you write this here and this is here, and if you rearrange this, then you can say it is a distinct, but it will be the same. So if you rearrange, then it will be distinct, but we will consider that arrangement is the same group, right? Because we have proved one result, that G cross H is isomorphic to H cross G. तो ये रीअरेंज करने से वो ग्रुप अलग नहीं हो जाता, वो आइसोमॉर्फिक ही रहता है. मीन्स आइसोमॉर्फिक मीन्स इट इज द सेम ग्रुप, राइट? सो let me give you one example. Suppose order of G is 30 and G is abelian. तो ये G का फॉर्म कैसा रहेगा? So G will be like this. G will be Z of some prime. So let 30 is what? 30 is 3 into 10, that is 3 into 2 into 5, right? So it will be Z3, or let me consider 90. So it is 3 square into 2 into 5. So order of G is 90, say. So it will be 3 square. So it is P raised to alpha 1, P1 raised to alpha 1. So P1 is 3, alpha 1 is 2. Then you may consider Z2 and Z5. So if you consider it this Cartesian product, then this is what? Cyclic group of order 9, cyclic group of order 2, cyclic group of order 5, and and 9 means it is a 3 square, that is prime raised to power. 2 raised to 1, that is prime raised to power, power is 1. 5 raised to 1, prime raised to 1 power. So every cyclic group is of order prime power order, right? So group of order 19 will be of the form this one, or you may have some another form also. You can say Z3 cross Z3 cross Z2 cross Z5, or you may have Z3 cross Z3 cross Z10. Sorry, no, not 10, because 10 will be what? 10 is what? It is not prime raised to power, so it is Z2 cross Z5, so it is the same one, right? So in short, this theorem says that every finite abelian group can be expressed as ADP of cyclic group of prime power order. ADP of cyclic group of prime power order. We will not discuss the proof of this theorem, but just we understand this, right? So this is one theorem, right? Now we state another theorem. तो ये theorem हमें क्या बता रहा है कि कोई भी finite abelian group है, then it can be expressed as EDP, external direct product of cyclic group. और वो जो cyclic group है उसका order भी कैसा है? Cyclic group of a prime power order. जो cyclic group है उसका order कैसा रहेगा? Prime का power, prime raised to some power. So we accept this result. Now the next result, and that is the fundamental theorem of finite abelian group. So let me start that result on that side. So okay, let me start here. Let G be a finite abelian group with order of G is equal to P1 raised to alpha 1 into P2 raised to alpha 2 into and so on into Pk raised to alpha k, where Pi's are distinct prime, and alpha I belongs to n. For I is equal to 1 to k, it is to be understood, and alpha I belongs to n. Then the number of non-isomorphic abelian groups, of order n. And what is n? N is the order of group. Okay, let me write here with order of G is n, and n is what? N is written in this way. So n is just this is what? It is just a prime factorization of n. So then the number of non-isomorphic abelian groups of order n is P of alpha 1, that is partition of alpha 1, and alpha 1 is what? It is some positive integer. So we know what do you mean by partition of alpha 1, total number of partition of alpha 1 into P of alpha 2 into and so on P of alpha k. So that is equal to, it is just product of P of alpha I is equal to 1 to k. So this theorem is known as the fundamental theorem of this theorem is known as fundamental theorem of finite abelian group. Fundamental theorem of finite abelian group. Okay, so let us try to understand. Okay, so let me just recall the previous theorem. Previous theorem था वो क्या कह रहा था कि suppose G is what? G is a finite abelian group and order of G is say n. It is a finite abelian group of order n. Then G is of the form, then G is of the form ZP1 raised to alpha 1 cross ZP2 raised to alpha 2 cross and so on ZPK raised to alpha k. And here PI's are prime, not necessary distinct, not डिस्टिंक्ट, वो अलग हो ऐसा जरूरी नहीं है, राइट। और ये थ्योरम क्या कह रहा है, व्हाट दिस थ्योरम सेज, लेट जी बी अ फाइनाइट अबेलियन ग्रुप और उसका ऑर्डर n है और यू जस्ट एक्सप्रेस n एज द n इन द प्राइम फैक्टराइजेशन, n का प्राइम फैक्टराइजेशन कंसिडर करो, then here you consider the prime factorization of n, so all primes are distinct, all primes will be distinct, and the number of non-isomorphic abelian group of order n is what? It is a product of partition of alpha I, and where alpha is are the indices which are used in the prime factorization of n of a distinct prime. So let us try to understand this result with an example. So for example, you consider, let order of G is, let us consider a simple example, 2 square. So here P1 is 2 and alpha 1 is 2. So order of G is 4 and G is abelian, and G is abelian. तो ये रिजल्ट क्या बोल रहा है कि then the number of non-isomorphic abelian groups of order 4 is product of I equal to 1 to k p alpha I. So here only p alpha 1, I have only 1, so it is p alpha 1, but here alpha 1 is what? Here alpha 1 is 2, because here are 2 square, so n is equal to also p1 is 2. Let me write here. Here if you compare, it is like with p1 raised to alpha 1, then p1 is 2 and alpha 1 is also 2, right? So p of alpha 1, that is p of 2, and that is what? 2. So there, then the number of non-isomorphic abelian groups of order 4 is p alpha 1, that is 2 ओनली. तो आपको 4 ऑर्डर का जो अबेलियन ग्रुप है ऐसे नॉन आइसोमॉर्फिक ग्रुप कितने मिलेंगे? ओनली 2. वन इज व्हाट? वन इज Z4 इज अबेलियन ग्रुप ऑफ ऑर्डर 4 and Z2 cross Z2 it is also a group of order 4 and it is abelian because Z2 abelian, so Z2 cross Z2 is abelian. तो ये एक ग्रुप हुआ और ये दूसरा ग्रुप हुआ, राइट? ये कैसे फाइंड किया है मैंने, दैट विल आई विल एक्सप्लेन विथ n number of examples, but right now just to understand, G is a group of order 4 and G is abelian, then according to this result number of non-isomorphic abelian groups of order 4 is product of p alpha 1, p alpha 2 up to p alpha k, and here only we have alpha 1 only, p1 alpha 1, here that is k equal to 1 only, so it is p alpha 1 and p alpha 1 means p2 and p2 means 2. तो मुझे दो ही ऐसे ग्रुप मिलेंगे कि जिसका ऑर्डर 4 है और वो अबेलियन है. नाउ देर आर ओनली टू नंबर ऑफ नॉन आइसोमॉर्फिक ग्रुप्स. सो दिस वर्ड इज इंपॉर्टेंट, नॉन आइसोमॉर्फिक अबेलियन ग्रुप्स. मतलब दुनिया भर में से कोई भी 4 ऑर्डर का अबेलियन ग्रुप लाएंगे आप, देन इट मस्ट बी आइसोमॉर्फिक टू आइदर दिस वन और आइदर दिस वन. ये दोनों नॉन आइसोमॉर्फिक है. सी Z4 has one element of order 2, one element of order 4, but Z2 cross Z2 has no element of order 4. Z2 cross Z2 कैसा रहेगा? Z2 cross Z2 is what? It is of the form 0 0 0 1 1 0 and 1 1. This is Z2. तो इसका ऑर्डर 1 है, इसका ऑर्डर 2, इसका ऑर्डर 2 and इसका ऑर्डर 2. So there is no element of order 4, but in Z4 there is an element of order 4. So these two are not isomorphic. तो कोई भी 4 ऑर्डर का ग्रुप लेंगे आप, वो अबेलियन है, देन आइदर इट विल बी आइसोमॉर्फिक टू दिस वन, मतलब ये Z4 जैसा होगा या इनके जैसा होगा. कोई तीसरी कैटेगरी का, मतलब कोई 4 ऑर्डर का अबेलियन ग्रुप है और वो ऐसा भी नहीं है और ऐसा भी नहीं, ऐसा नहीं बनेगा, राइट. सो यू मस्ट हैव एनी अबेलियन ग्रुप ऑफ ऑर्डर 4. It is either of the form this one or this one, right? So let me give one more example. और ये स्टेटमेंट मैंने क्यों लिखा साइड में, क्योंकि एनी अबेलियन ग्रुप, ये थ्योरम क्या बोल रहा है कि एनी फाइनाइट अबेलियन ग्रुप कैन बी एक्सप्रेस एज प्रोडक्ट ऑफ साइक्लिक ग्रुप ऑफ प्राइम पावर ऑर्डर. तो ये 4 ऑर्डर का ग्रुप था, देन इट इज व्हाट, इट इज ईडीपी ऑफ cyclic group of prime power order. So it is 2 is prime, 2 raised to 1, 2 raised to 1, and here pi's are not necessarily distinct, here primes are equal, right? So let me give one more example. See, you consider let G be abelian group of order 36. G is abelian. So 36 is what? It is a 6 square. That is, it is a 2 square into 3 square. So according to this theorem, how many non-isomorphic abelian group of order 36? So number of non-isomorphic abelian groups of order 36 is equal to, so you compare this is with p1 raised to alpha 1 into p2 raised to alpha 2. So it is product of p of alpha I is equal to 1 to 2. Here alpha 1 is 2 and alpha 2 is also 2. That is what? It is p of 2 into p of 2. P of 2 is what? 2 into 2. Partition of 2, 1 plus 1 and 2. So there are 2 partition of 2. Total number of partition of 2 is 2. So it is 2 into 2 is 4. तो क्या मतलब हुआ? Number of non-isomorphic abelian group of order 36 is equal to 4. तो मतलब आपको 4 ही ग्रुप ऐसे मिलेंगे 36 ऑर्डर के, जिसका ऑर्डर होगा 36, वो अबेलियन होंगे, and that 4 are non-isomorphic, right? And what are that 4 groups? So let me list out that 4 groups. So one group will be this one, Z2 cross Z2 cross Z2 cross Z2 cross Z2 cross Z3 cross Z3. This is one. Another one is Z2 cross Z2 cross Z9. Third one will be Z4 cross Z3 cross Z3, and fourth one is Z4 cross Z9. So if you see, then order of this group is 2 into 2 into 3 into 3, that is 36. Here 2 into 2 4, 4 into 9 36, 4 into 3 12 into 3 36, 4 into 9 36. तो ये चारों के चारों ग्रुप का ऑर्डर क्या है? 36. All 4 are abelian because all Zn's are abelian, so they are abelian. So I have 4 groups, 1 2 3 and 4 groups. ये कैसे मैंने फाइंड किए? आई विल एक्सप्लेन हाउ टू फाइंड दिस, बट दिस आर 4 abelian group of order 36. और one more thing, it is what? It is EDP of cyclic groups of prime power order. 2 raised to 1, 2 raised to 1, 3 raised to 1, 3 raised to 1, 2 raised to 1, 2 raised to 1, 9. 9 means it is 3 square, so it is prime power order. 4 means 2 square, 3 raised to 1, 3 raised to 1, 2 square, 3 square, right? तो मतलब ये जो थियरम है वो भी यहाँ पे वेरीफाई हो रहा है कि एनी फाइनाइट अबेलियन ग्रुप कैन बी एक्सप्रेस एज प्रोडक्ट ऑफ कैन बी एक्सप्रेस एज एक्सटर्नल डायरेक्ट प्रोडक्ट ऑफ साइक्लिक ग्रुप ऑफ प्राइम पावर ऑर्डर. और इस थियरम से हमें पता चल रहा है कि ये 36 ऑर्डर के नॉन आइसोमॉर्फिक ग्रुप कितने मिलेंगे? तो दैट इज 4. सो व्हाट डू यू मीन बाय नॉन आइसोमॉर्फिक ग्रुप्स? तो ये ग्रुप, ये बाकी के जो तीनों ग्रुप है उसके साथ वो आइसोमॉर्फिक नहीं है. मतलब ये ग्रुप, रफली स्पीकिंग, देन दिस ग्रुप इज नॉट लाइक this one or this one. Why? You can verify. In this group there is no element of order 9. इस ग्रुप में आपको 9 ऑर्डर का कोई एलिमेंट नहीं मिलेगा. Why? In fact you will not get any element more having order more than 6. क्योंकि Z2 में जो एलिमेंट है उसका ऑर्डर आइदर 1 और 2, ईयर 1 और 2, ईयर 1 और 3 और ईयर 1 और 3. तो 1 और 3, 1 2 3, तो इन तीन नंबर में से 1 2 एंड 3 में से किसी का भी कॉम्बिनेशन करेंगे आप, देन यू विल नॉट गेट द एलसीएम इज 9, राइट? सो दिस ग्रुप डज नॉट कंटेन एनी एलिमेंट ऑफ ऑर्डर 9, बट दिस ग्रुप हैज वन एलिमेंट ऑफ ऑर्डर 9. You consider identity and 1, so that element has order 9. So this group and this group is not isomorphic. Now if you look at here, then this group has an element of order 4, but this group does not have any element of order 4, so this and this will not be isomorphic. This group has an element of order 9, but this group does not have any element of order 9, so this group is not isomorphic to this one or this one. तो ये ग्रुप, ये तीनों में से किसी के साथ आइसोमॉर्फिक नहीं. बाय सेम आर्ग्यूमेंट यू कैन शो दिस ग्रुप विल नॉट बी आइसोमॉर्फिक टू दिस वन. ये तो नहीं है इसके साथ, क्योंकि ये इसके साथ आइसोमॉर्फिक नहीं है, तो ये इसके साथ आइसोमॉर्फिक नहीं है. नाउ Z4, इसमें हियर देयर इज नो एलिमेंट ऑफ ऑर्डर 9, बट हियर एलिमेंट ऑफ ऑर्डर 9, तो ये दोनों आइसोमॉर्फिक नहीं है. नाउ what about with this one? Here there is no element of order 4. यहाँ पे 4 ऑर्डर का एलिमेंट नहीं है, यहाँ पे 4 ऑर्डर का एलिमेंट है, right? And so this group and this group is not isomorphic. Now these two will not be isomorphic because here there is an element of order 4, but here there is no element of order 4, right? तो मतलब ये जो चारों ग्रुप है वो एक दूसरे के साथ आइसोमॉर्फिक नहीं है. So these are 4 non-isomorphic group. Now if you consider any group of order 36 and if it is abelian, then that group must be isomorphic to one of them. वो 36 ऑर्डर का ग्रुप या इसके जैसा होगा या इसके जैसा होगा या इसके जैसा या इसके जैसा. ये 4 टाइप के ही हो सकते हैं, इसके सिवा कोई दूसरी टाइप नहीं हो सकती अबेलियन ग्रुप की जिसका ऑर्डर 36 हो, राइट? सो दैट इज द मीनिंग ऑफ दिस थियरम, राइट? ओके, यहाँ पे जो मैं बोल रहा था कि इसमें 9 ऑर्डर का एलिमेंट है, यहाँ पर नहीं है. लेट मी एक्सप्लेन कि कैसे यहाँ पे एलिमेंट रहेगा और ये नहीं रहेगा. सो Let me remove this theorem statement. See, Z2 cross Z2 cross Z3 cross Z3, then Z2 cross Z2 cross Z9, Z2 Z4 cross Z3 cross Z3, Z4 cross Z9. Let me say this is G1, this is G2, G3 and G4. So order of G1 equal to order of G2 is equal to order of G3 is equal to order of G4, and it is 36, first of all. Now see, you consider one element from here, 0, 0 and 1. The order of 0 in Z2 is 1, because see, Z2 is what? Z2 is 0, 1. So order of 0 is 1 and order of 1 is 2. And in Z9, what I have? 0, 1, 2 up to 8. So order of 0 is 1 and order of 1 is 9, because 1 is what? It is a generator. So its order is 9. Right? So I will consider 0, 0 and 1. So if I consider say this is alpha, then order of alpha is what? It is what? It is LCM of order of 0, order of 0 and order of 1. That is LCM of 1, 1 and 9, and it is 9. तो मतलब क्या हुआ? I have one element alpha is equal to 0, 0, 1 of order 9 in G2. लेकिन ये G1 में कोई 9 ऑर्डर का एलिमेंट नहीं है. Why it is not? लेकिन why? Because in Z2 cross Z2 cross Z3 cross Z3, तो यहाँ पे Z2 में कौन से ऑर्डर के एलिमेंट है? आइदर ऑर्डर 1 और 2. Z2 इज 0 और 1, तो उसमें 1 ऑर्डर का एलिमेंट है या 2 ऑर्डर का एलिमेंट है. सिमिलरली हियर 1 और 2. इन Z3 में क्या रहेगा? 0, 1 एंड 2. 0 का ऑर्डर 1, 1 का ऑर्डर 3 एंड 2 हैज ऑल्सो ऑर्डर 3. राइट? सो हियर possible order of element of Z3 is 1 or 3. Here also 1 or 3. So if you consider any element, say beta belongs to here, and suppose beta is of the form A, B, C, D, then order of beta is what? It is LCM of order of A, order of B, order of C and order of D. So LCM of what? The value of A, B, C, D will be what? Either all are 1, some are 1 and remaining are 2, some are 1 and remaining are 3, some are 2, remaining are 3, means 2 and 3, all are 2 or all are 3. So its LCM will never be 9. मतलब in 1 or 2 or 3 के combination ले लो कोई भी, so you will never get the LCM is 9. तो मतलब for any beta from here there is no element of order 9. So मुझे G2 में एक 9 ऑर्डर का एलिमेंट मिल रहा है, G1 में वो 9 ऑर्डर का एलिमेंट अवेलेबल नहीं है. So G1 is not isomorphic to G2. By the same argument, G3 में क्या रहेगा? What is in G3? Z4 cross Z3 cross Z3. So here possible order of element of Z4 are 1, 2 or 4. Here 1 or 3 and here 1 or 3. So if you consider any element of G3, then it is of the form A, B, C. Then possible order of A, B, C are 1 2 4. For A 1 2 4, for B 1 3, and for C 1 or 3. So if you consider any combination from here, then you will not get LCM is 9. So there is no element of order 9 here, right? So G2 and G3 are also not, G2 is not isomorphic to G3, तो ये भी isomorphic नहीं रहेंगे. So G1 is not isomorphic to G2, G2 is not isomorphic to G3. Now here in G3 there is an element of order 4. G3 में 4 ऑर्डर का एलिमेंट है. कैसे बनाएंगे आप? यू कंसिडर वन आइडेंटिटी, one from Z4 and 0 0. So 1 belongs to Z4, 0 belongs to Z3, 0 belongs to Z3, 0 का order 1, 0 का order 1 and 1 का order 4. So order of this element, say it is delta. So order of delta will be LCM of order of 1 0 and 1 0, that is order LCM of 4 1 and 1. So it is LCM of 4 1 and 1, and that is 4. So G3 contains an element of order 4, but G1 and G2 does not contain any element of order 4. Why? Because in G1 in here what I have written G1, so there is no combination which gives me the LCM 4. So like that G1 and G3 is not isomorphic, and similarly G4 contains an element of order 4, but G1 does not contain. So G1 and G4 is not isomorphic. So by that way you can say these 4 groups are non-isomorphic. हर एक का order क्या है? G1, G2, G3 and G4 has order 36. They are abelian, but they are not isomorphic. मतलब ये सब अलग अलग टाइप के ग्रुप है, right? Now if you consider any group of order 36 and it is suppose abelian, then it will be one of the form this. वो किसी न किसी एक के जैसा ही होगा. कोई पांचवा आपको ग्रुप नहीं मिलेगा कि जो इससे अलग हो, वो अबेलियन हो और उसका ऑर्डर 36 हो. ऐसा नहीं मिल सकता. सो दैट इज द फंडामेंटल थियरम ऑफ फाइनाइट अबेलियन ग्रुप. ओके, सो नाउ लेट अस सी हाउ टू लिस्ट दिस 4 ग्रुप्स. सपोज मुझे 36 ऑर्डर का ग्रुप दे दिया है, तो 36 ऑर्डर के 4 नॉन आइसोमॉर्फिक ग्रुप मिलेंगे. दैट वी नो बाय दैट फॉर्मूला, प्रोडक्ट ऑफ पी ऑफ अल्फा आई. यू जस्ट कंसिडर द prime factorization of 36. You just find out alpha i's, then consider its partition, then find out just its product. So that will be the what total number of non-isomorphic group of order 36. But how to list these 4 groups? So let us see. तो ये मैंने कैसे लिस्ट किए थे. So how to find non-isomorphic groups? How to find all non-isomorphic groups. How to find all non-isomorphic groups of given order. How to find non-isomorphic abelian groups. Abelian groups of given order. So let us start with order 36 as we discussed. So let order of G is equal to 36 and G is abelian, and G is abelian. So first of all, what you consider, order of G is 36, so you just first of all find out prime factorization of that n order. So it is what 2 square, that is 4, into 3 square, that is 9. So you just compare it with p1 raised to alpha 1 into p2 raised to alpha 2. So here p1 is equal to 2, p2 is equal to 3, alpha 1 is equal to 2 and alpha 2 is equal to also 2, right? Now कितने मिलेंगे? So that is 4. So product of p of alpha I, that is I equal to 1 to 2. So it is p of alpha 1 into p of alpha 2, that is p of 2 into p of 2, that is 2 into 2, that is 4. तो इतने नॉन आइसोमॉर्फिक ग्रुप्स मिलेंगे 4. कैसे फाइंड करेंगे? सो फॉर दैट you concentrate on first factor, that is 2 square, and here 3 square, 2 square, 3 square. So you consider p1 raised to alpha 1, p2 raised to alpha 2. Now you look at the power alpha 1, alpha 2. Here in our case it is 2. So you look at 2. Similarly here you look at 2. Now you just write down the partition of this 2. So partition of 2 is 1 plus 1 and 2. Here partition of 2 is 1 plus 1 and 2. Suppose here I have 3, then I will write the partition of 3, 1 plus 1 plus 1, 1 plus 2 and 3. Suppose here I have 4, then I will write the partition of 4, 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 3, 4 and 2 plus 2. So but here I have 2 and 2. So you just write down the partition. Now I will make the pair. This with this partition, this is first pair, and corresponding to this 1, 1, 1 and 1, what I will write? Z, here 1, and this 1 is a partition of these 2, and this 2 is a power of 2. So 2, and here I have 1 and 1. So Z 2 cross Z2, and here power is 1. This 1 and 1. Corresponding to this partition, this is a partition is corresponding to this p2 raised to alpha 2. So there are two integers 1 and 1, two parts. So you consider Z cross Z, but 1 this is corresponding to 3 square, and here due to this 2 we have 2, so you consider here 3 and 1 1. So it is 1 1. So this portion is corresponding to this one, and this portion is corresponding to this one, and you just take its cross product, right? So no need to write this 1 power. So it is 2 2 3 3. So this is one group, and its order is 36. 3 into 3 9, 9 into 2 18, 18 into 2 36. Now I will make a pair 1 plus 1 and with this 2. So corresponding to this 1 1, the pair is what? Z. This 1 1 is partition of 2, and the base of this 2 is prime 2. So you consider 2 cross Z2 and power 1 corresponding to this. Now cross here 2. So this 2 is a partition of this 2, and this base of this 2 is 3. So you consider Z 3, and its power is this one 2. So it is 3 square, and you can write Z 9 also, but you keep as it is. Now you fix this 2 and consider pair with this 1 1. So this partition and this partition. So corresponding to this partition, this 2 is a partition of this 2, and base of this 2 is this prime 2, so it is Z2, and power should be this one 2, so it is 2, cross 1 plus 1, so corresponding to 1 plus 1 what I have, so this 1 plus 1 is a partition of these two, and the base for this 2 is 3, right? So here I will write Z3 cross Z3 and 1 1, so here 1 and 1, right? And for this 2 and this 2 second, so this is Z, this 2 is it is a partition of these two, and base for this 2 is this 2, so it is 2 and 2, so it is a square, cross Z 2, so this 2 is what? Partition of this 2, and the base for this 2 is 3, so it is 3, and partition is 2, so it is square. So if you rewrite, then it is what? It is just, this is equal to Z, I just remove the indices, so Z2 cross power, so it is Z2 cross Z2 cross Z3 cross Z3, and this one is Z2 cross Z2 cross Z3 square, that is 9, this one is Z2 square, that is 4 cross Z3 cross Z3, and this one is Z4 cross Z9. So in this way we have this for non-isomorphic abelian group of order 36. So let us understand with one more number. So let me consider order of G is say 144. Order of it is 144. So order of G is 144. So it is 2 raised to 4, and it is 3 square. 144 is what? It is 12 square. 12 is what? 4 into 3 square. So it is 2 raised to 4 into 3 square. So 2 raised to 4 into 3 square. So here P1 is 2, P2 is 3, alpha 1 is 4, and alpha 2 is what? Alpha 2 is 2. Fine. Right. So product of P alpha I. So it is a P of 4 and P of 2. P of 4 is 5 and P of 2 is 2. So it is 10. So there will be 10 non-isomorphic groups of order 144. So let us list out all these 10 groups. So 4 and 2. So here you consider alpha 1 partition, that is, let me write in this way, 2 raised to 4. So from 2 raised to 4 you look at 4, this 4. From 2 raised to 4 you look at 4, and from here 3 square you look at 2, right? Now you look at the partition of 4. So partition of 4 are 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 3, 4 and 2 plus 2. So 1, 2, 3, 4 and 5 partitions. Now partitions of 2. So it is 1 plus 1 and 2. तो आप इस पार्टीशन के साथ इन दोनों की पेयर, इसके साथ इन दोनों की, इसके साथ इन दोनों की, इसके साथ इन दोनों की और इसके साथ इन दोनों की. सो देयर आर 10 pairs. In this way you will get 10 groups. तो कैसे लिखेंगे? So corresponding to this 1 plus 1 plus 1 plus 1, और आप इसको ऐसे भी लिख सकते हैं. See, you just write down 3 square and you look at the partition of 2 here, and it is 1 plus 1 and 2. So let us try to write down in some different way. See, 1 1 1 1. So first of all, this is what it is corresponding to 2 raised to 4, and here base is the prime in the base is 2. So corresponding to here 1 2 3 4. So you just write down Z2 cross Z2 cross Z2 cross Z2. Now right now forget about this portion. You forget about this portion. You just concentrate here. So corresponding to this portion, you just write down Z2 cross Z2 cross Z2 cross Z2. How many? 1 2 3 4 times. So 1 2 3 4 times. Now your power is 1 1 1 1 1. So power is 1 1 1 1. Right? Now here 1 2 3. So you just write down Z2 cross Z2 cross Z2. 1 2 3 3 times. So 1 2 3. Now what is the power? 1 1 and 2. 1 power and 2 power. Right? Now 1 3. So only 2. So Z2 cross Z2. 1 and 3. So power is 1 and 3. Here 4, only 1. So it is Z2 only 1 times. And power is 4. Here 2 plus 2. So Z2 cross Z2 2 times. Power is 2 and 2. 2 and 2. And you can verify 2 into 2 into 2 into 2, 16. 2 square, that is 4 into 2, 8 into 2, 16. 2 cube, 8 into 2, 16. 2 raised to 4, 16. 2 square, 4. 2 square, 4. 4 into 4, 16. So order of every group is 16. And 2 raised to 4 is also 16. Right? Now corresponding to this 2 partition, 1 1. But this 1 1 is a partition of 2, and the base for this 2, that is alpha 2, is prime 3. So here 2 times you write down Z3 cross Z3, that is Z3 cross Z3, and power is 1 1. So 1 1. Now 2, so only 1. So it is Z2, Z3, and power is 2. So now you have 1 2 3 4 5, and here 2. So now you just consider the EDP of this with this one and this one. So you will get two groups, this into this one. So let me write here, it is this one into this one, that is Z2 cross Z2 cross Z2 cross Z2 cross Z3 cross Z3. Now this is Z2 cross Z2 cross Z2 cross Z2 cross Z9. 3 square is 9. Now this one, so it is what? Z2 cross Z2 cross Z2 square, 2 square is 4, cross Z3 cross Z3, and similarly Z2 cross Z2 cross Z4 cross Z9. So these two. Now with this one, it is Z2 cross Z2 cube, that is 8, cross Z3 cross Z3, this one. And now with this one, that is Z2 cross Z8 cross Z9. Now with this 2 raised to 4, that is Z16 cross Z3 cross Z3, and Z16 cross Z9. And with this, so we have these two, and last one is Z2 square, 2 square is 4. So Z4 cross Z4 cross Z3 cross Z3, and this is Z4 cross Z4 cross Z9. So these two. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 non-isomorphic groups of order 144 and they are abelian. तो मतलब दुनिया में से कोई भी ग्रुप उठा के आएंगे आप जिसका ऑर्डर 144 हो और वो अबेलियन हो, देन इट मस्ट बी वन ऑफ द फॉर्म अमोंग दिस ओनली. इसी में से किसी एक को आइसोमॉर्फिक हो जाएगा. सो दैट्स व्हाई वी से दीज आर नॉन आइसोमॉर्फिक. ये ग्रुप इनमें से ये जो फर्स्ट वन है, इट इज नॉट आइसोमॉर्फिक टू रिमेनिंग 9. दिस वन इज नॉट आइसोमॉर्फिक टू रिमेनिंग 9. ये किसी के आइसोमॉर्फिक नहीं है इनमें से. दिस वन इज नॉट आइसोमॉर्फिक टू द रिमेनिंग 9. सो दीज आर नॉन आइसोमॉर्फिक. ये मतलब सब अलग अलग ग्रुप है. इसके अलावा कोई मैंने ग्रुप लिया, राइट, देन इट मस्ट बी वन ऑफ द मस्ट बी आइसोमॉर्फिक वन ऑफ द ग्रुप. So this is the way to list out the non-isomorphic group. So what is the algorithm? First of all, you just write down the prime factorization of your order. Then you consider what is the alpha 1, alpha 2. Then just find out the number of partition of alpha 1, alpha 2 and so on, and just find out the product. So whatever the product of partition of alpha is, it will gives you the total number of non-isomorphic group of order n. Then how to write? So you just write down the partition of each p1 raised to alpha 1 corresponding to p1 raised to alpha 1, p2 raised to alpha 2. You find out alpha 1, alpha 2, write down its partition. Then corresponding to alpha 1, you just write down the EDP of cyclic group of prime power order. Similarly for alpha 2, and just consider all possible combination. Okay, so let us illustrate one more. Let me say order of G is 72. Order of G is 72. So order of G is 72. It is 12, 6, and 12 is what? 2 square into 3 into 2 into 3. So it is 2 cube into 3 square. Okay. So here alpha 1 is 3 and alpha 2 is alpha 1 is 3 and alpha 2 is 2. So number of non-isomorphic abelian groups of order 72 is equal to P of 3 into P of 2, and P of 3 is what? Partition of 3. Oh sorry, partition of 3 is 3. 1 plus 1 plus 1, 1 plus 2 and 3. So partition of 3 is 3 and partition of 2 is 2. So there are 6. So you will have 6 non-isomorphic group of order 72. कैसे फाइंड करेंगे? सो ये 2 क्यूब में से आप निकालो 3 दिस पावर एंड 3 का पार्टीशन 1 plus 1 plus 1, 1 plus 2 and 3, and then you look at the 3 square में से 2. Now 2 का पार्टीशन 1 plus 1 and 2. Now corresponding to this, and here base is 2, so here I will write 3 times Z2. ये 2 कैसे आया? यहाँ से. यहाँ पे बेस प्राइम क्या है? P1 it is 2, so it is Z2 cross Z2 cross Z2 and 1 1 1. So here 1 1 and 1. Now here 1 plus 2, here 2 terms. So it is Z2 cross Z2 2 times. Here 1 power is 1, no need to write 2, so power 2. And corresponding to 3, only one term in the partition, so it is Z2 only one time and power is 3. and for here corresponding to this one, two terms, so I will write Z3 cross Z3, and here 2 I will write Z3 and 2, 3 square. So you just consider the all possible Cartesian product, EDP, sorry. So this one into this cross Z3 cross Z3, this one cross Z3 square, this one cross this one, this one cross this one, and this one cross this one and this one. So 3 into 2, 6. So you will get that 6. So let me list all that 6 is Z2 cross Z2 cross Z2 cross Z3 cross Z3, then Z2 cross Z2 cross Z2 cross Z3 square, 3 square is 9. Now from here Z2 cross Z4, 2 square is 4, cross Z3 cross Z3, then Z2 cross Z4 cross Z9, then 2 cube is 8, so it is Z8 cross Z3 cross Z3, then Z8 cross Z9. So I have this 1, 2, 3, 4, 5, 6 non-isomorphic group of order 72 and all are abelian. Okay, so now I want to discuss one more thing, and that is what वो हमने लाग्रांजिस थियरम जब पढ़ा था तब हमने we had discussed that converse of Lagrange's theorem is not true. What is Lagrange's theorem? If order of G is n, means G is a finite group, and if H is a subgroup of G, then order of H divides order of G. So that is the Lagrange's theorem. And what is the converse? If G is a finite group, and if suppose K divides order of G, then there exists a subgroup of G of order K. So that is not true in general, but it is true for finite abelian groups. वो हमने स्टेटमेंट दे दिया था विदाउट प्रूफ, बट फ्रॉम हियर वी कैन प्रूव दिस, राइट, बट विल नॉट प्रूव, वी विल जस्ट वेरीफाई. सपोज लेट G be a group of order 72 and it is say abelian. Now 12 divides 72 and that is order of G. Now suppose I want to find a subgroup of G of order 72, of order 12. So I want to find H subgroup of G and order of H is 12, राइट. 72 का डिवाइजर है 12, तो मुझे 12 ऑर्डर का उसको सब ग्रुप चाहिए, राइट. तो यहाँ से मुझे एक चीज़ क्या पता चले कि G मेरा अबेलियन है. G is what? G is abelian. Okay, so first let me clear one thing. Converse of Lagrange's theorem is true for finite abelian group, और वो हम यहाँ पे वेरीफाई कर रहे हैं, राइट. तो ये मेरा G फाइनाइट 72 ऑर्डर का अबेलियन ग्रुप है और 12 उसका डिवाइजर है. So I want to show that if G is a abelian group of order 72, then it must have a subgroup of order 12. तो यहाँ से ये क्या है? So let me say this is G1, G2, G3, G4, G5 and G6. So what is this G1 to G6? ये G1 to G6 ऐसे ग्रुप है जो नॉन आइसोमॉर्फिक है और हर एक का ऑर्डर कितना है 72, और कोई भी 72 ऑर्डर का ग्रुप लेंगे आप और वो अबेलियन है, देन इट मस्ट बी आइसोमॉर्फिक टू, इसी में से किसी को आइसोमॉर्फिक हो जाएंगे. मतलब 72 ऑर्डर का कोई भी अबेलियन ग्रुप इनमें से ही किसी के जैसा है, राइट, बिकॉज इट इज द लिस्ट ऑफ नॉन आइसोमॉर्फिक अबेलियन ग्रुप ऑफ ऑर्डर 72. तो अब मैं ऐसा दिखा दूं कि ये G1, G2, G3, G4, G5 and G6 all has a subgroup of order 12, then we are done, right. क्योंकि कोई भी मैं 72 ऑर्डर का अबेलियन ग्रुप लूँगा तो वो किसी न किसी एक के साथ वो आइसोमॉर्फिक हो जाएगा, और मैं ऐसा दिखा दूंगा कि ये हर एक को 12 ऑर्डर का सब ग्रुप है। मतलब कि वो जो मेरा 72 ऑर्डर का कोई भी अबेलियन ग्रुप है उसको भी 12 ऑर्डर का एक सब ग्रुप है। सो दैट इज द आइडिया। सो नाउ आई विल शो ऑल G1 to G6 हैज अ सब ग्रुप ऑफ ऑर्डर 12। तो कैसे दिखाते हैं, सी फ्रॉम हियर what you consider, 12 ऑर्डर का चाहिए, राइट। सो लेट मी रिमूव दिस थिंग। Z1 क्रॉस Z2 क्रॉस Z2 क्रॉस Z2 क्रॉस 3 times Z2, then Z3 cross Z3. So this is your G1. Now what you consider, okay, so see 3 into 2, 3 into 2 6, 6 into 2 12, तो इनका प्रोडक्ट 12 हो जाता है, राइट। सो व्हाट आई कंसिडर, यू कंसिडर singleton 0 is a subgroup of Z2. Z2 is a subgroup of Z2. Z2 is a subgroup of this Z2. Z3 is a subgroup of this Z3. And singleton 0 is a subgroup of this Z3. Right? So this cross this cross this cross this is a subgroup of this one. So let me say this is, say, H1. So what is the order of H1? So H1 is a subgroup of G1, and order of H1 is what? Order of this one, that is 1, order of this one, that is 2, order of this 2 is 2 into 3 into 1. So it is 12. तो क्या हुआ, ये H1 is a subgroup of G1 and order of H1 is 12। मतलब कि ये G1 के पास 12 ऑर्डर का सब ग्रुप मिल गया, राइट। नाउ यू कंसिडर G2। सो व्हाट इज G2? इट इज Z2 क्रॉस Z2 क्रॉस Z2 क्रॉस Z9। दिस इज योर G2, राइट। ओके, नाउ we know that if you consider Zn, this is one result from Zn. If you consider Zn, then for every positive divisor D of n, there is exactly one subgroup of order D of Zn। मतलब Zn में n के हर एक पॉजिटिव डिवाइजर के ऑर्डर के बराबर का उसको एग्जैक्टली एक सब ग्रुप मिलता है। दैट इज द रिजल्ट इन Zn, वी हैड डिस्कस, राइट। तो यहाँ पे Z9, सो ईयर 3 डिवाइड्स 9, तो मतलब Z9 के पास एक 3 ऑर्डर का एक सब ग्रुप है, ये हमने प्रूव किया था, राइट। तो Z9 के पास एक 3 ऑर्डर का सब ग्रुप है। सो लेट H बी ए सब ग्रुप ऑफ, लेट मी राइट हियर, let H be a subgroup of Z9 and order of H is 3. So H is a subgroup of Z9 and its order is 3। ऐसा मुझे subgroup मिलेगा, right? Now Z2 is a subgroup of Z2. This Z2 is a subgroup of this Z2, and singleton 0 is a subgroup of this Z2. So this cross this cross this is a subgroup of this one, and let me say it is H2. So what is order of H2? Order of H2 is order of this singleton 0, that is 1, into order of Z2 is 2, order of Z2 is 2, and order of H, and it is 3. So 3. So it is 12. तो मतलब H2 is a subgroup of G2 and its order is 12, तो मतलब G2 के पास भी 12 ऑर्डर का सब ग्रुप है. So similarly I will show that G3, G4, G5 and G6 has. So let us quickly do it. So let me go with G3. So let me rough this. Z2 cross Z4 cross Z3 cross Z3. This is your G3. So here what I will do, here 4 into 3 is 12. So I will consider Z2 singleton 0 is a subgroup of Z2 cross Z4 is a subgroup of Z4, Z3 is a subgroup of Z3 and singleton 0 is a subgroup of Z3. So this cross this is a subgroup of G3. Let me say it is H3. So order of H3 is what? 1 into 4 into 3 into 1, that is 12. And H3 is a subgroup of G3, right? So G3 is a subgroup of order 12. Now what about G4? It is Z2 cross Z4 cross Z9 is equal to, it is G4. So as I discuss here, Z9 has a subgroup of order 3. Z9 के पास 3 order का एक subgroup है, right? So let me say it is H, the same one. So H is a subgroup of Z9 and order of H is 3 cross Z4 is a subgroup of Z4 and singleton 0 is a subgroup of Z2. So 0 cross Z4 cross H. So this will be a subgroup of this, and let me say it is H4. So what will be order of H4? It is 1 cross 4 cross order of H is 3. So it is 12. मतलब H4 is a subgroup of G4 and order of H4 is 12. मतलब G4 के पास भी एक 12 order का subgroup है, right? Now what about G5? Z8 cross Z3 cross Z3. This is your G5. Now Z8 के पास there is, let me say K. K is a subgroup of Z8 and order of K is 4. Z8 के पास 4 divides 8. 4 divides 8, तो Z8 के पास 4 ऑर्डर का सब ग्रुप होगा, मिलेगा उसका. So you consider that K is a subgroup of Z8 and its order is 4, and Z3 is a subgroup of Z3 and singleton 0 is a subgroup of Z3. So this one cross this one is a subgroup of G5, and let me say it is H5. So what is order of H5? It is the order of K, that is 4, order of Z3 it is 3 and order of singleton 0 is 1, so it is 12. So H5 is a subgroup of G5 of order 12. मतलब G5 के पास भी 12 order का subgroup है. And finally G6. So that is Z8 cross Z9. तो Z8 के पास एक 4 order का subgroup है because 4 divides 8, and Z9 के पास एक 3 order का subgroup है. So let me say that 4 order subgroup is K. So K is a subgroup of Z8 and its order is 4, and H is a subgroup of Z9 and its order is 3. So K cross H is a subgroup of this one, and this is your G6, and let me say it is H6. Then order of H6 will be what? Order of K, that is order of K is 4, and order of H is what? 3. So it is 12. राइट तो मतलब H6 के पास भी 12 ऑर्डर का एक सब ग्रुप है. सो व्हाट वी हैव प्रूव्ड, G1, G2, G3 अप टू G6 ऑल हैज अ सब ग्रुप ऑफ ऑर्डर 12, राइट. और ये जो G1 टू G6 है वो क्या है? दैट इज द ऑल नॉन आइसोमॉर्फिक अबेलियन ग्रुप ऑफ ऑर्डर 72. मतलब दुनिया का कोई भी 72 ऑर्डर का कोई भी ग्रुप है, अबेलियन है, तो किसी न किसी एक से वो आइसोमॉर्फिक हो जाएगा. और इन सब के पास 12 ऑर्डर का सब ग्रुप है, तो वो जिसके साथ भी आइसोमॉर्फिक होगा तो उसके पास 12 ऑर्डर का सब ग्रुप है. तो वो जो 72 ऑर्डर का सब ग्रुप था, अबेलियन ग्रुप, उसके पास भी 12 ऑर्डर का सब ग्रुप है. सो हियर वी हैव स्टार्टेड विथ 72 and we have considered one divisor 12 of 72. So you can think about any divisor of 72 and you just verify, or you go in this way, then you can find suppose 36 is a divisor of 72. So you can also construct a subgroup of order 36 in each case. Similarly, 2 is a divisor of 72, so you can always find out a subgroup of order 2 from G1 to G6. So this is what it is, just a verification of converse of Lagrange's theorem. But this is what, this is a technique. ये जो मैंने ये 12 के लिए जो एक टेक्निक डेवलप की, सो इफ़ यू राइट इन सम mathematical manner, proper manner, then it will be the proof that converse of Lagrange's theorem is true for the finite abelian groups. Okay, so this is what fundamental theorem for finite abelian group and converse of Lagrange's theorem for finite abelian group. Okay, so if I summarize all this discussion of this lecture, then if you have any finite abelian group, then it can be expressed as external direct product of cyclic group of prime power order. That is first thing. Second thing, if order of G is n, and if n is expressed as a prime factorization, that is p1 raised to alpha 1, p2 raised to alpha 2 up to pk raised to alpha k, then number of non-isomorphic abelian groups of order n is equal to product of partition of alpha I equal to 1 to k. And third thing, converse of Lagrange's theorem is true for finite abelian groups, and that is what if order of G is n and G is abelian, and if k divides n, then there exists a subgroup of G whose order is k. So that's what we have in this lecture. So we stop this lecture here, and in next lecture we'll see some application of this fundamental theorem of finite abelian group for UN. So we stop this lecture here. Thank you.